have seen one method of source coding, that is Shannon Fano code method. So there are two methods given in your syllabus, Shannon Fano code method and the Huffman coding. So one method we have already seen in previous lecture. So there are some drawbacks of Shannon Fano code method. So we will see those drawbacks first here. So first drawback, that is this method is ambiguous method, and ambiguity arises due to availability of more than one equally valid scheme for partitioning. We know the methods or steps used for the Shannon Fano code method. In that, what we were doing, we were partitioning all the given messages with a decreasing order. We were first arranging those messages according to decreasing order of probability, and then we used to partition those messages with the equiprobable set. So here, during the partition, there may be chances of arising ambiguity due to availability of more than one equally valid scheme for partitioning. Means there may be chances of getting more than one scheme for partitioning, so that causes the ambiguity in this method. And also, as the number of messages increases, this method is not suitable, and formation of m approximately equiprobable group is rather difficult, which and that gives us a very little choice for partitioning. So with the number of increased messages, means value of m is increased with different probabilities. So in this method, Shannon Fano code method, that method become very tedious and left us a little choice for partitioning. And also here, this Shannon Fano code method in Shannon Fano code method, efficiency reduces as the number of messages increases. So these are the some drawback of Shannon Fano code method, and to overcome these drawbacks, we are using the second method of source encoding, that is the Huffman coding method. So we will see this method now. Huffman coding method gives the lowest possible value of L. What is L now? Capital L is the length of code word which we are preparing or finding using this different coding methods. So this method, Huffman coding method, gives lowest possible value of capital L, that means code word length, for a given m messages, resulting in maximum efficiency or minimum redundancy. We know the efficiency and redundancy are inversely proportional to each other. So in this method, by giving this method gives us a possible lowest value of the code word, that gives the maximum value of coding efficiency eta, and the minimum value of redundancy, we can say. And hence this method, because of that, this method is also called as a minimum redundancy code or optimum coding technique. Okay, so we will see how we can generate a code word of a lowest possible value using the Huffman coding method. So likewise, like that Shannon Fano code method, here also we have some steps to follow in Huffman coding. So we will see those steps to generate the code word using Huffman coding method. So first step is same. We have to list out all the source symbols or the messages given in order of decreasing probability. Then the second step, second step is the two source symbols of lowest probability are assigned numbers 0 and 1. So the two messages with the lowest probability, find those two messages in a given list, and assign zeros and 1 to those messages. Now these two source symbols or messages are combined into new messages. We have to combine those two messages with the least probability into one new message, and the probability of that new message will be equal to summation of the probabilities of two original messages or symbols. Now the probability of this new message is placed in a list according to its value. Whatever value I am getting after adding those two probabilities of previous messages, the new probability value you have to place in to a probability list according to its value. Suppose it value is same, if we have same value message already, then give this new message probability first priority or top priority. Then repeat this procedure until we are left with only two source symbols for which a 0 and 1 are assigned. Okay, so we have to repeat this step till we are left with the two messages to which we can assign zeros and 1. Okay, so we will see numerical on this. With the help of numerical, this method can be easily explained. So we will see this numerical. Suppose in numerical we have given 5 messages m1, m2, m3, m4 and m5 with the probability values 0 0.4, 0 0.2, 0 0.2, 0 0.1, 1 respectively. So how we can generate a code word using Huffman coding method for this problem. And once we get the code word, we can find the code length and we can obtain the value of coding efficiency, entropy easily. Okay, so just follow the steps given here in Huffman coding algorithm or Huffman coding method. So first step we have in this method, that is we have to arrange all the messages according to decreasing order of probability. So these messages are already given in decreasing order of probability, and we have to list out. We have to list out the message with the lowest probability value. So M4 and M5, these are the two messages with the lowest probability value. So point 1 and point 2, point 1 and point 1 and point 1. These two messages or these two probability values we can combine to form a new message. So new message is obtained by combining M4 and M5, and the new probability value will be summation of these two probabilities, point 1 plus point 1, which will be equals to point 2. Okay, so this is my new message. Now I have to uh, place the new message probability in my probability list value. So in second column or in second stage, again arrange those probability values, but now we already have two message with the same probability value, point 2, that is M2 and M3. These two messages already have the same value, so give the new message probability highest priority compared to this previous existed messages. So now in second column or in second stage, we can write messages with a decreasing probability, point 0.4, point 0.2, point 0.2, and these two messages are the original messages M2 and M3. So also write down the path for that message, where my M2 is traveling from this point to this, M3 is traveling from this point to this, and this new message generated is here. Okay, then repeat the same stage for the next two messages with the lowest probability value. Now here we have lowest probability value messages are M3 and M4, so we can combine these two messages and we can add their probabilities to get a new probability value for the new message. So probability value for that message will be 0.2 plus 0.2, that is equal to 0.4, and assign 0 and 1 to those messages. Okay, so now in next step, the simplified diagram for this, I can write the next new probability value here, new probability value, that is the addition of this previous two messages with the lowest probability. Then write this 0.4, draw the path for these previous messages. Okay, in this way. Now follow or repeat the same stage until we are left with the two messages. Okay, so after repeating the same stage, now in third stage again I am getting two messages with the probability least probability value as 0.4 and 0.2. I can add those two messages and the probability will be 0.6, so I can write here 0.6 in fourth stage on the top, and then this 0.4 message, that is M1 message with a 0.4, this first message in third stage as it is, and now assign 0 and 1 to this two last messages. Okay, so we are getting here this diagram for Huffman coding. Now how we can generate the code? This step is very important to generate or to write code from the given diagram. Okay, so how we can write code? So to write code here, start from the last stage, that is from fourth stage, and trace back to the stage 1 along the reverse path and write code word in terms of 0 and 1 starting from stage 4 to stage 1. Okay, so for every message you have to start from last stage to first stage till we reach that particular message. Okay, so we have to follow path for that particular message to write the code word for that message, and the path should be reversed from fourth stage to last stage, sorry, from last stage to first stage. So to write code word for M1, so we will follow the path here. See, for M1, see, my M1 is traveling from point 4, then this point 2, okay, then from here to here. Now the code, to write the code word, sorry, this is not the path for M1. For M1 the path is this, okay, point 4, then this and this. Okay, so we have here, if we follow the reverse path, so in reverse path, what I'm getting in reverse path, I have this 0, assign this those zeros in reverse path. Okay, this is my path, so in reverse path we have this 0, okay, this 0, and we have here another 0, okay, write that 0. So code word for M4 will be 0 0. Okay, means you have to just identify the path from either first to last stage or last to first stage, and to write code word you have to move from last stage to first stage. So if we move from last stage to first stage till M1, I'm getting the digit in terms of zeros and 1 are 0 0. Now to find path for M2, where is my M2? So path for M2 will first go in forward direction and then in backward direction. Okay, so this is my path for M2. So for M2 I have here, if I move in reverse direction for on the same path, I'm getting here this one and here this one, sorry, this, not this one and this 0, because we are considering the this upper message. Okay, means this point to value and this point to value are same. This point to value is shifted from this first column to second column here, and we have assigned 0 to that column. So we have to write here code word for this second message M2. We can write that message as 1 and 0. Okay, so code word for that M2 we can write this message, okay, 1 and 0. That is the code word for second message. So this is the code word value for second message. Similarly, we can write the code word value for third message by selecting this reverse direction path, and we can write down code word for each message, okay, by traveling in reverse direction from last to first stage. Okay, and we can obtain those values of zeros and 1. So here I am getting code words for M1 as 0 0, for M2 as 1 0, for M3 as 1 1, for M4 as 0 1 0, and for M5 as 0 1 1. Okay, so code length we can write LK for each message. Code length represents the number of bits present in the code word. So we have 2 bits in first message. Okay, so code length will be 2. For second, third message again we only have 2 bits. So code word length for this 2 also 2. For fourth and fifth message we have 3 bits in code word. So message length or code word length will be 3 in this case. And from the equation of code word length, we already know this equation, which is summation of pk into lk. So we can obtain the value of code word length by putting this value from this table. So probability values are already given. Code word length we have obtained from this Huffman coding, and if we put those values, we will get here length of the code word, that is 2.2 bit per message. Okay, now the entropy value again we can calculate using this formula pk, summation pk log to the base to 1 by pk, where k goes from 1 to 5. We have 5 messages in this given numerical. So after calculation I am getting here entropy value is 2.12193 bit per message. So efficiency we can calculate using the formula eta equals to h by l. Put those values obtained in calculation into 100. So I am getting here efficiency value as 96.4%, and the redundancy value also we can calculate, which is 1 minus the efficiency, so we will get that value as a redundancy value. So that's how we can calculate the code word length, and we can find out efficiency for given messages using the Huffman coding method also. Okay, so these are the two source encoding methods, that is Shannon Fano code method and the Huffman code method. These are the two methods we have in syllabus for source coding. The next point in this module we are going to see, that is the channel capacity theorem. Okay, see, we have two parts are there in digital communication system: the source encoder and the channel encoder. So source encoder uses source encoding technique for encoding that message. Now here channel encoder is used for channel encoding, means to reduce the effect of noise, and redundancy bits are added. So based on that, uh, this channel encoder is used for that purpose. So we will see here theorems based on channel capacity. So first theorem, that is Shannon channel capacity theorem. So in this theorem, suppose we have given R as a transmission rate, where transmission rate represents the number of bit transmitted by the source, and if C is the channel capacity, which represents the value of bit or capacity of a channel, which carries channel capacity represents the number of bits carried by the channel. If by Shannon channel capacity theorem, if R is less than or equal to C, then there exists a coding technique such that the output of the source may be transmitted over the channel with the probability of error in the received message, which may be made arbitrarily small. So this is the statement for Shannon channel capacity theorem. What this statement states, means in summary we can write this statements as: for R less than or equals to C, that means when transmission rate is less than or equal to channel capacity, the error free transmission is possible in the presence of noise. That means here we can say, when the transmission rate is less than the channel capacity of any channel, then the error free transmission is possible even in the presence of noise. Okay, so that is the statement for first theorem of on channel capacity, that is the Shannon channel capacity theorem. Then the second theorem is given here, that is we have second theorem in syllabus, that is Shannon Hartley channel capacity theorem. So what this theorem states, that to state the channel capacity of a continuous bandwidth Bz having an additive wide Gaussian noise of a power spectral density n0 by 2 over a limited bandwidth, it is given by this channel capacity is given by the equation C equals to B log to the base to 1 plus S upon n0 B. The units are bits per second. Okay, so channel capacity is given, it is related to bandwidth. Channel capacity, this Shannon Hartley channel capacity theorem state that the channel capacity is related to bandwidth, and we can write the equation for channel capacity when we have given the additive wide Gaussian noise power spectral density as n0 by 2. So channel capacity equation we can write using the Shannon Hartley channel capacity theorem as C equals to B log to the base to 1 plus S upon n0 B. Okay, so if the channel capacity of a wide band limited Gaussian channel is n, the channel capacity, the same equation we can write for wide band limited Gaussian channel is C equals to B log to the base to 1 upon log to the base to 1 plus S by n bits per second, where this S by n is a signal to noise ratio, that B is the channel bandwidth, S is the average transmitted signal power, and n is the noise power within the channel bandwidth. Okay, so in presence of additive wide Gaussian noise, we have that n as n0b, and here in wide band limited Gaussian channel we have replaced that n0b by the noise spectral density. Okay, so these are the two channel capacity theorem we are having in syllabus. So this was the last topic in this module, and this module is finished here. Assignments will be given on this module, so complete that assignment before deadline. Thank you.